In this video, we will be doing some examples with 2's complement. 2's complement can be used to convert and represent negative numbers from decimal to binary and vice versa. Let's try an example. For number 1, we are being asked to convert negative 95 decimal to 2's complement with an 8-bit representation. The first step is to take the absolute value of the number. In this case, we are taking the absolute value of negative 95, which is 95. The next step is to write out the binary representation of the number. So we have that 95 in decimal can be written as 1011111 in binary. Because we want an 8-bit representation, we are going to add a 0 in on the left to be the most significant bit. This does not change the value of the binary number. It only uses extra bits to represent it. So again, the binary value for 95 using an 8-bit representation is 0101111. The next step is to flip the bits. So this means that all of the 1s will become 0s and all of the 0s will become 1s. This turns our number 0101111 to 101000000. After we flip the bits, we need to add the number 1 to that new value. So the math we are doing is 101000000 plus 1. So we do 0 plus 1 is 1, and then there's no remainder or anything to carry over, so the rest of these numbers can just be brought down as normal. This leaves us with the 2's complement representation 101000001. Notice how the most significant bit of this value is a 1, which tells us that the decimal number for this 2's complement number is in fact negative. Therefore, to write negative 95 using the 2's complement, the number would be 101000001. In these next examples, we will be converting from 2's complement to decimal. Please see Part B, Example 1, where we are being asked to convert 11010011 2's complement to a normal decimal number. Since we are told that this is a 2's complement representation, we can check the most significant bit to figure out if the number in decimal is going to be positive or negative. In this case, the most significant bit is a 1, so we know that the decimal number we are searching for is going to be negative. If the most significant bit had been a 0, we would just be able to convert from binary to decimal as normal, as this decimal number would just be a positive number. But since our most significant bit is a 1, which is a negative decimal number, we're going to have to flip the bits and add 1, and then convert to decimal, and then negate the decimal value that we find. You can see these steps here for both scenarios. So the number we are given is 11010011 2's complement. So the first step is to flip the bits. So all of the 1s will become 0s and all of the 0s will become 1s. This will give us the new number 001001100. Next we have to add 1 to that number. So 0 and 1 gives us a 1, and then there's nothing to carry over, so the rest of these numbers are just brought down as normal, as if they were being added to 0. The next step is for us to figure out what this binary number is in decimal, so we convert over. Now, as is, this number really represents the value 45, but because the 2's complement number that we started with, the most significant bit was a 1, we know that it's really representing negative 45. Part B, Example 2, is asking us to convert 01010011 2's complement to decimal. So this 2's complement value that we are given has a most significant bit that is a 0. So if we refer back to our steps over here, if the most significant bit is 0, which represents a positive decimal number, we can simply convert to decimal as is. So in this case, we have 0101, 0011, which is the binary representation for the value 83. So 0101, 0011 2's complement is equal to 83 in decimal.